Hi girls, today we are going to see about hysteresis. What is hysteresis? When a ferromagnetic material is kept in a magnetizing field, the material gets magnetized by induction. That is, suppose if we take ferromagnetic material, that is iron, nickel, cobalt, like that, and if we keep it in a magnetizing field, the metal gets magnetized, so the material will become magnetized. And here an important factor is that when you see this graph, and here along the x-axis you are having magnetizing field, along the y-axis you are having flux density. Flux density is nothing but magnetic field, and so here when you apply magnetizing field, the material gets magnetized. So when you increase the magnetizing field, the graph will go like this, that is along AC. So when gradually increase the magnetizing field, the flux density also increases, and this is the saturation point. After reaching this point, if you decrease the magnetizing field, it will not retrace the path, but it will move in the path CDE. So it will go along the path CDE when you decrease the magnetizing field. And when you see at this point D, here the magnetizing field is 0, that is you are not applying any field, that is the magnetizing field is stopped. Because the value of magnetizing field here is 0, but still you are having some magnetic field, magnetism in the substance. That is, even after removing the magnetizing field, the material is having some magnetism, and so this portion is called retentivity. And you see this diagram, this portion AD is called retentivity. That is, when the magnetizing field is 0, but still you are having magnetic field. Now you are applying, slowly you are decreasing the magnetizing field, it will go the path DE, and here the complete magnetism will become 0. So the magnetism is now become 0, and here when you again decrease, it will retrace the path EF, and the path when you increase in the positive direction, it will go along the path FGKC until this again reach this saturation point. And so here this closed loop is called hysteresis loop, and the area will be different for different materials. And so here first we are going to see very important definition, retentivity and coercivity. What is retentivity? And retentivity is the residual magnetism AD. The residual magnetism means the remaining magnetism. Residual means remaining. So the residual magnetism AD present in the specimen is called remanence or retentivity. It is defined as the ability of the material to retain the magnetism in them in magnetizing field vanishes. That is, magnetizing field vanished, but still it retained the magnetism. This is called remanence or retentivity. And what is coercivity? Coercivity is the magnitude of the reverse magnetizing field for which the residual magnetism of the material vanishes is called coercivity. That is, for what field the residual magnetism becomes 0. So for that particular value, the residual magnetism 0, and this is called coercivity, and this is represented in the graph. And when you see this graph, this AD is called retentivity and this AE is called coercivity. And here you are having residual magnetism. Here the residual magnetism completely vanishes for a particular value of magnetizing field. So throughout these cases, hysteresis means it hesitate. Hesitate is a form word from hesitation. Hesitation means, you know the meaning of hesitation, that is lagging. That is a phenomenon of lagging of magnetic induction behind a magnetizing field is called hysteresis. So in all this loop, you can find out that magnetic induction lags behind the magnetizing field, that is B lagging behind H. Hysteresis means lagging behind. Now we shall see about hysteresis loss. Because of this, the residual magnetism, there is some loss. So this is due to the rotation and orientation of molecular magnets in various directions. So the molecular magnets are orienting and reorienting in different direction, and because of that only you are having this hysteresis loss. This loss is given by the formula delta E is equal to integration over a closed circle H vector dot dB vector. And here this delta E is energy loss, and you know H is a magnetizing field and dB is magnetic induction. And for B the unit is ampere meter square, and for H you know ampere per meter. All these values you already know. And delta E is energy which is in joules. And this is about hysteresis. Now depending upon that we are segregating the ferromagnetic materials into two types, hard and soft magnetic materials. So hard materials can be used for some purposes and soft magnetic materials can be used for some other purposes. And usually the soft magnetic materials with a smaller area and hard magnetic materials will have larger area. With larger area. So when you see this diagram, you are again drawing hysteresis loop, and you see this blue curve, this is smaller in area, and you see this red line, this is having larger area. So the smaller area is usually called soft magnet, whereas for larger area the magnets are usually called they are hard magnets. And when you see the properties are different. So first column soft ferromagnetic material and the second column hard ferromagnetic materials. When you give external field and when you remove that, magnetization completely disappears, but here the magnetization persists means continues. Here the area is small, here the area is large, that you know. And retentivity, coercivity, both are low for soft and high for hard. And what about susceptibility and magnetic permeability? It is a reverse, that is high in soft and low in hard ferromagnetic materials. Here the loss is less, here the loss is more. And uses soft ferromagnetic materials can be used in solenoid core, transformer core and electromagnets, whereas hard ferromagnetic materials can be used as permanent magnets. And some examples are given: soft iron, mu metal, stellite. And for hard steel, alnico and lodestone. These are examples for hard ferromagnetic materials. And so here the applications of hysteresis loop, and the hysteresis loop is mainly used so that you can find out the retentivity, coercivity, permeability and susceptibility and energy loss for each material. And from this you can find out what are the applications: permanent magnets, electromagnets and core of the transformers. Permanent magnet means the materials with high retentivity, high coercivity, high permeability, everything is high in permanent magnet. Example: steel, alnico. That is in the tabular column the same is given. Here it is given in different subtitles. And here electromagnets means high initial permeability, low retentivity, low coercivity and thin hysteresis loop. They are used as electromagnets, and depending upon their nature they can be used in different fields. And here the examples are soft iron, mu metal or nickel ion alloy. And core of the transformers. Core means you know transformer is having primary coil and secondary coil, and inside this there is a core. This core is usually made up of material which is having high initial permeability, large magnetic induction and thin hysteresis loop with smaller area, that is used to design transformer cores. And here the example is soft iron. So only soft iron can be used as a core of the transformer. So this is about the applications of hysteresis loop. Next we are going to see about magnetic effects of current, that you know, that is whenever current flows through a loop the magnetic effect is there. So here Christian Oyster, he done a lecture in physics and noticed that electric current passing through a wire deflects the nearby magnetic compass. So when you see this diagram you can understand. Here this is the key, and this key, here the wire is carrying current, and this is the compass box. When the switch is on the off position, that is the switch is here not in the on position, that is the current is not flowing. So when the current is not flowing, the magnetic needle is like this, that is in 0 0 reading. And when you switch on, that is when you put the switch, then what happens? The current flows. As soon as the current flows, the magnetic needle is deflected. So which shows that there is deflection, that is when current flows through any loop, some magnetic field is created there. Because of that, the compass needle deflects. Suppose if the current direction is reversed, then the magnetic needle will deflect in the opposite direction. So this property of current is mainly used in several purposes, and electric, magnetic, combinedly they are called as electromagnetism, because electric and magnetic, they are not individual topic, but they are totally together can be studied as electromagnetism, because they cannot be separated. So this is about magnetic effect of current, and that's all. Next we are going to see about magnetic field around a straight current carrying conductor and circular loop. And here this is a simple experiment. Here this is a cardboard, and in the cardboard you are making a hole and you are inserting a wire. Through this wire the current is passed, and these black, they are iron filings. So when the iron filings are kept on this horizontal board, and you pass the wire, and you simply taper the board. So first you tap the board, that means you make a small shaking, and what happened, the iron fillings arrange themselves in concentric circles around this. These concentric circles are nothing but magnetic lines of force. When you see this diagram, you can understand. Here this is the direction of current. Current is flowing in the wire in this direction, and the iron fillings are arranged in concentric circles around the wire. So this is the experiment which you have studied in lower classes. And so here the needle of the magnetic compass experiences a torque. So usually when you keep any compass box near a magnetic carrying, that is a current carrying conductor, it experiences a torque and deflects to align to the direction of the magnetic field at that point. So it will tend to align with the field. And so when you see the pattern, you can see the concentric circles having their center at the axis of the conductor, as you see in the diagram. So if the strength of the current is increased, then the density of the magnetic field will also increase, and it depends upon only the strength of the field. The strength of the magnetic field decreases at a distance or from the conductor. And so when you see this diagram, when you move from the center, the magnetic field density slowly decreases. That you know, because as we go away from this current carrying wire, the magnetic field definitely decreases. And the next is circular coil carrying current. And here instead of one hole, you are making two holes, and these two holes, a wire is wounded, and here there are so many turns in this wire, and you can take it as 10 or 50 turns will be like this. And here these black are nothing but iron filings, and when you pass a current through this wire, the iron filings will arrange in this pattern. So here the pattern is different. When you see this diagram, these are two holes A and B. Through this the wire is passed, and here at A the iron filings will arrange in this concentric circles, at B in this form, whereas in between A and B they will have a uniform magnetic field which is shown by this line. And this shows a circuit diagram, that is the coil is connected with key, rheostat and the battery. Through the battery only you are sending the current. Here the current flows in clockwise direction. Suppose the direction is reversed, then the direction of this magnetic lines of force also changes. So this is due to this is along the compass needle. That is, suppose we keep a magnetic compass near a current carrying circular conductor, then the needle of the magnetic compass experiences a torque, the same point as I have studied earlier, and deflects to align in the direction of the magnetic field at that point. Here, and when you see at the center of the coil, the magnetic field is uniform, almost uniform. So this is shown by the straight line, and here the north pole and south pole depends on the direction of current in the loop. So it is always determined by the direction of current. Next we are going to see about right hand thumb rule. And in a right hand thumb rule, you hold your right hand like this, and in this the thumb represents the direction of current, and here these are the direction of other fingers. When you curl that are curling around this wire, this direction of fingers represents the direction of magnetic field. So right hand thumb rule usually gives the direction of magnetic field. And so when you see the statement, if we hold the current carrying conductor in our right hand. So we are taking a current carrying conductor in right hand such that the thumb points in the direction of current flow, then the fingers encircling the wire points in the direction of the magnetic field lines produced. So once again I will explain this. And so here this is your right hand and you are keeping a wire in this direction. Here the thumb is the direction of current, that is the current is flowing upwards, then the direction of these fingers will give you the direction of magnetic field. So this gives the direction of magnetic field. And next we are going to see about Maxwell's right hand corkscrew rule. And here this is very simple. You take a screwdriver like this, you are moving rotating the screwdriver in the upward direction, then the direction of rotation of the screw will give you the magnetic field. So here the screw advances in this direction, that is, you imagine you are removing a screw from a particular place. So the direction of the screw will be in the upward direction, whereas the direction of rotation gives the magnetic field. So this rule is used to determine the deflection of the magnetic field, that is the direction of the magnetic field. And here the statement is, if we rotate a right-handed screw using a screwdriver, then the direction of the current is the same as the direction in which the screw advances in the direction of rotation of the screw gives the direction of the magnetic field. So this is about Maxwell's right-hand corkscrew rule. Next to Lorentz force. Lorentz force means when an electric charge Q is kept at rest in the magnetic field, no force acts on it. So you are keeping a charge in a magnetic field, no force acts. So when will the force act? When the charge moves. So when the charge moves, definitely there will be some force. So it experiences a force, and this force is called a magnetic Lorentz force, and given by F vector is equal to Q into V vector cross B vector. This is the formula used, and this force is nothing but Lorentz force, where Q is the charge which is moving, V is the velocity of the charge, and B is the magnetic field. And here this is the cross product. So this is very important equation. F vector is equal to Q into V vector cross B vector. And there is some mistake in this equation, so you leave it. And next we are going to see about force on a moving charge in a magnetic field. That is, we are going to see about the properties of this force. And you know, Fm vector is equal to Q into V vector cross B vector. This is cross product or vector product, you know. When you expand this, you will get QVB sin theta. Here always the velocity is perpendicular to the magnetic field. So when an electric charge Q is moving, the velocity V vector in the magnetic field B vector, it experiences a force which is called magnetic force, and these two, that is velocity and the magnetic field, this velocity and magnetic field, they are perpendicular to each other. That is a natural phenomena. And so here they are, since they are perpendicular, this theta will become 90 degree. You know, sin 90 is equal to 1. And here the properties are, there are some 7 properties of magnetic Lorentz force, which is very important. You remember the equation, write the properties. So first F, you know, BQV, and so F is directly proportional to magnetic field, and it is directly proportional to velocity, and it is directly proportional to sine of the angle between the velocity and magnetic field. So these 3 properties are from the equation, because F is equal to, you know, BQV sin theta. So it is directly proportional to the 3 factors, and also F is directly proportional to the magnitude of the charge Q. And next, when you see this diagram, when you see this is negative charge and this is positive charge, here the force, magnetic field and velocity, they are making an angle theta, and F is in the upward direction. Suppose if the charge is positive, then the direction is reversed. This is in the downward direction. This is the main, so direction of Lorentz force on positive charge and negative charge. And here the direction of Fm vector has always perpendicular to V vector and B vector, as M vector is, M is the cross product of V vector and B vector. Also always the V vector and B vector, they are perpendicular to each other. And this is 5th property, and you change it. This is 6th property, and this is 7th one. Here the direction of Fm vector, negative charge, is opposite to the direction of Fm vector, as positive charge provided other factors are identical, that is their direction is opposite, that you should know. That is for the direction of positive charge and the direction of negative charge will vary. And if the velocity of the charge q is along magnetic field and v are in the same direction, means theta will become 0, so the force will become 0, because you know sin 0 is equal to 0. And next we are going to see about definition of Tesla. Tesla is a unit for magnetic induction, and so the definition is the strength of the magnetic field is 1 Tesla if unit charge moving in it with unit velocity experiences unit force. So unit charge moving with unit velocity experiences unit force, that is called 1 Tesla. So 1 Tesla is 1 Newtons 1 Coulomb, and the velocity is ms power minus 1, and this s will go in the numerator. So 1 Tesla is equal to the 1 force 1 Coulomb 1 velocity. So this is the formula. When you simplify this, you will get 1 n a power minus 1 m power minus 1. This is another format, because 1 Tesla you know force by cm, that is Newton by cm, where c represents the unit for charge and m represents the distance, that is velocity is ms power minus 1, that is substituted here. Next, motion of charged particle in a uniform magnetic field, and here these are crosses. These crosses represent that a magnetic field is acting in this direction, it is moving inwards to the paper, so that is denoted here B vector inwards. And here when you take this positive charge will move in the circular path, and usually the velocity is drawn as tangent, and the force is always acting towards the center, so the force is called centripetal force. So here the crosses represent the magnetic field acting inwards, and this charge is moving with the velocity v vector, and here we are going to derive an expression for magnetic time period and frequency. And usually the velocity is perpendicular to the magnetic field, and so the magnetic Lorentz force becomes F vector is equal to q into v vector cross b vector, and so you can leave this, you can directly write, this is not needed, Fm is equal to bqv, because sin theta will become 1, because theta is equal to 90 degree. This Lorentz force is equal to centripetal force. Why centripetal force? Because the particle executes circular motion. So you can substitute centripetal force mv square by r. From this, r is equal to mv by qb, and this mv is nothing but momentum. So you can replace mv by magnitude of linear momentum of the particle. And so here, what is time period? Usually time is distance by velocity. When you take the perimeter of a circle, that is 2 pi r, so t is equal to 2 pi r by v, and you can substitute for r here. From this equation you substitute r, so you will get t is equal to 2 pi m by qb. And here what is frequency? Frequency is a reciprocal of time period, so you can reciprocate this equation right here. This is called cyclotron period. And what is omega? Omega is angular frequency. Angular frequency is having the formula 2 pi f. Here omega is angular frequency, whereas f is frequency. You can substitute for f and you will get qb by m. So this is angular frequency, where q is the charge, b is magnetic field, and m is mass of the particle. In all these equations, you can have only q by m, that is the charge by mass ratio, and other things are not there, that is velocity and radius, or these factors are not involved in this equation. Thus you can understand that the frequency derived is called cyclotron frequency or gyro frequency, and as I told you, the time period and frequency depend only on the charge to mass ratio, but not velocity or radius of the circular path, because these two values are not included in the equation, the derived equation. So usually we assumed that the velocity and magnetic field is perpendicular. Suppose the case when the velocity is not perpendicular to the magnetic field, then the velocity is split up into two components, parallel component and perpendicular component. The parallel component will have no any force, that is remain unchanged, whereas the component perpendicular to the field keeps changing due to Lorentz force. So here the parallel to the field remains unchanged, whereas the perpendicular component will move according to Lorentz force. And so here when you see, this is a magnetic field, and here the path is not circular as you seen above, but here the path is helical in nature. So this is helical when the velocity is not perpendicular to the magnetic field. And when you see this diagram, this is one experiment that is called Wilson cloud chamber. In this, the path is visible here by any method, that is usually the condensation of water is taken here, and so here the path is visible, and here the path is helical in nature. This will take place when the velocity is not perpendicular to the magnetic field. So far we have seen about